Students, in part of the video, we are going to learn about electromagnetism. Before 19th century, people thought that electricity and magnetism are two different subjects. But by the experiments of Ørsted, it is found that they could be treated as a single one. And that branch of physics is known as electromagnetism. We can learn the properties of electricity and as well as the magnetism. Before knowing about the experiments of the Ørsted, we have to know some basics about that. Electricity. Electricity can be classified into two parts. You know that. One is the static electricity and second is the current electricity. Static electricity explains about the charges which are at rest, and it explains about the fields due to the charges which are at rest, and you know that charges always lies over the surfaces. The second thing, current electricity, explains about the flow of the charges in a particular direction. Even though they are flowing in a particular direction, we can't say electricity, that means electric current is not a vector quantity. Do remember that. Here in these experiments, what we are taking the steady current, and here see what could happen. But when we take the steady current, see the first circuit which is here. First of all, what we did, we marked north, south and east, west directions. Then we took a circuit. If you watch this circuit, you will find what a source of potential. It is the battery, or you can say a cell, and it is connected to a rheostat. What is rheostat? Rheostat is a variable resistor, and it is connected to a key, and the two ends of this conductor, say it as A and B, and we took a compass needle. Actually, a compass needle named as NS is pivoted on a sharp edge, and it is what parallel to the AB. When in steady state, you can't get any deflection in this magnetic needle. It leads to the experiment. Accidentally, I said what he did, he pressed the key and he found that a deflection in the magnetic needle. What he did, he pressed the key and he found a deflection in the magnetic needle. If you watch it carefully, you will find here when current is flowing from south to north, see, I showed the directions, current is flowing. Okay, here is the positive terminal and the negative. Current is flowing like this. Okay, here he found that the magnetic needle, that means this one, deflected towards the west. The needle deflected towards the west. When he released the key, he found that again it is aligned along AB, along with the AB. Then again he pressed it and he found the same result. Then after he used the rheostat, gradually he increases the resistance and he found that the deflection is less when the resistance is increased. That means what? He moved this key and he just kept here up to here. The resistance offered is increased. He get less deflection in, and he moved this key up to here. The needle up to here. That means what? Less resistance is offered in the circuit and he get the more deflection. Again, by releasing that, he found the same result and he came to a conclusion. Whenever current flows through a conductor, something is happening which leads to the deflection in the magnetic needle. What is that something? Here you learn that if you take the two magnets and keep the similar poles near to each other, then we found that what? They get repelled with each other. If you keep the unlike poles, that is north and south or south or north, near to each other, they get attract. That means around a magnet, a magnetic field is set up. Here in the same way, when current is flowing through this conductor, what? That something is the magnetic field is formed around this coil and it makes the magnetic needle to move. With that, he came to a conclusion that when current flowing through a conductor, a magnetic field will be set up. And he didn't stop there. He changed the polarity. See this diagram. In this one, what happening? See, it is the direction of the current. He pressed the key and he observed that the needle deflected in opposite direction. Here in that one, it deflected towards the west, and in this case, it deflected towards the east. When he released the key, he got the same result. Again, the deflection becomes zero. And by changing the resistance, he observed that the deflections are varying. When the resistance is less, more current flows to this conductor, then the deflection is more. When the resistance is increased, what is that? Less current will flow, then the deflection will be less. Here, these are the observations of Mr. Oersted, and we call them as the Oersted experiments. And about the Oersted's experiments, and we found that whenever current flows through a conductor, around a magnetic field will be set up. Okay, and the magnetic needle which is kept below the current conductor got a deflection, and you observe that. Now we are talking about magnetic field and as well as the Lorentz force. Magnetic field. This magnetic field also known as magnetic flux density or magnetic field strength. What is the magnetic field? You have to understand. Magnetic field is the amount of force acting on a unit north pole which is kept in a magnetic field. Magnetic field strength is the amount of force acting on unit north pole which is kept in a magnetic field. Here we are going to talk about the magnetic field effect on the charge. Magnetic field's effect on the charge. Let's take a three-dimensional plane. Name them as X, Y and Z axis. Okay, and this frame is imagined is kept in a uniform magnetic field which has the induction of B. Say it is the B. Magnetic field, the magnitude of the magnetic field is B. And uniform magnetic field. What is uniform magnetic field? It is the field where the intensity of the field is same at all places. It is a field where the intensity of the field is same at all places. What does it mean? Here, every place in that field has same kind of intensity. And already we learned that the lines of forces in uniform magnetic field appears to be parallel to each other. And already I told you, a uniform magnetic field is always a part of the non-uniform magnetic field. Non-uniform magnetic field, maybe it's shown like this. Okay, it's a non-uniform magnetic field. Take a stretch of that and you will find these lines appears to be parallel to each other. That's why a uniform magnetic field is always associated with the non-uniform magnetic field. Keep that thing in mind. Just imagine that a charged particle just enter into the magnetic field, making an angle of theta with the field. Here in this way a charged particle is moving. Let the charge is q and it's entered with a velocity of v bar, and it is making an angle of theta with the magnetic field B. Then we will see what happens. Here, to understand that concept very easily, we have to remember the concept of dot product. Here, when we are learning about the dot product, when two vectors are taken as A bar and B bar, the dot product is written as A bar dot B bar is equal to AB cos theta. It's the dot product of the two vectors. Here, if you watch it carefully, here is the B is a field and velocity is also a vector. We are taking the dot product of that. Let's see what happens. It is entered in and the charged particle is moving with a velocity of v bar. So it experiences a force. We have to find out the magnitude of that force. The force which is acting on the charge, which is kept in the magnetic field, is known as the Lorentz force. Okay, if you watch the diagram carefully, you will find is the velocity of the charged particle which is moving in this way, and we are resolving the velocity into components. Let's take this component which is beneath the theta is v cos theta, obviously. Then this component is v sin theta. Here v cos theta and b are parallel to each other, and you know that the force is equal to Q is a charge. I did a mistake. To understand the concept of force acting on the charged particle which enters into the magnetic field making an angle of theta, we have to learn the basics of cross product. And you know that the cross product of the two vectors are written as like this: a bar cross b bar is equal to AB sin theta. AB sin theta. See what vectors we are taking is a b bar and v bar. The force, Lorentz force, can be written as F bar is equal to Q of v bar cross b bar. We are applying the same here. A bar b cross b bar is equal to AB sin theta. Similarly, v bar cross b bar is equal to VB sin theta. That is, the magnitude of the Lorentz force can be written as QVB sin theta. Okay, it is force experienced by charged particle when it is moving in a uniform magnetic field. Okay, that is F is equal to QEB sin theta. Freeze it. Now watch this. We are going with the situation. The case 1 I am taking. In case 1, I am taking theta is equal to 0. That means what? Instead of making an angle of theta with the B, this charged particle is moving in this direction. The Q. Then the angle between the B bar and Q is equal to how much? 0. Then F is equal to BQV sin theta. Theta is equal to 0. Then we can write it as BQV sin 0. You know that sin 0 is equal to 0. That is, force is equal to 0. This force is minimum. What it tells us, when a charged particle is moving along the direction of the magnetic field, it doesn't experiences any kind of force. Remember that when the magnetic field and the motion of the charge is parallel to each other, they are in the same line, then the amount of force experienced by this charge is equal to 0. Then we are taking one more case. In this case, we are taking case 2. Theta is equal to 90 degree. And you know that what happens now? F is equal to BQV sin theta. It is BQV sin 90. The force is maximum. That means what? If the charged particle is moving along this direction, that means instead of moving in this way, when it is moving like this, the force acting on the charged particle is 0. When it moves like this, perpendicular to the B, it experiences maximum force. It leads to another statement known as Fleming's left-hand rule. By using the Fleming's left-hand rule, you can find out the direction of the force which is acting on the charged particle which is kept in a magnetic field. Now we are going to learn about Fleming's left-hand rule. Here, Fleming's left-hand rule is used to find out the direction of the force acting on the charged particle which is kept in a magnetic field. It can be stated like this. Here it is the left hand, and stretch the fingers of the left hand in mutually perpendicular directions like this. See, it is the thumb, it is the pointer, and it is the middle finger. We are stretching 3 fingers mutually perpendicular directions. I am showing that here. Let's say it is thumb and it is the pointer, and third one, see, it is the middle finger, or central finger. They are mutually perpendicular to with each other, these 3. And see, here it is the direction of the magnetic field as shown before. Is the motion of the charge, is the Q, or you can say motion of the conductor. Then we have to find out what's the direction of the force acting on the conductor. If we say it is the charge or the conductor, here, see, it resembles that. Now listen to the statement. Imagine a person is holding his 3 fingers of the left hand in mutually perpendicular directions. Is the thumb, is a pointer, and it is the central finger. If the pointer is showing the direction of the magnetic field and the central finger is showing the direction of the charge, motion of the charge or the conductor, then the thumb shows the direction of the force which is acting on the charge. This is a Fleming's left-hand rule. Listen it carefully. A person stretched his 3 fingers in mutually perpendicular directions. What are those fingers? Thumb, pointer, and middle finger in mutually perpendicular directions, means each one is making an angle of 90 degree with the other. If the pointer is showing the direction of the magnetic field and the central finger is showing the direction of the motion of the charge, then the force experienced by the charge will be along the direction of the thumb. Understand? It is the Fleming's left-hand rule. It is nothing but cross product of 2 vectors. It's a cross product of 2 vectors. See this, the charge is moving, it is V and is the B. Both are is the vector A bar and it is B bar. Let the angle is 90 degree. Then the resultant might be this, C bar. C bar is equal to A bar cross B bar. Earlier we got a relation. If it is the F force and it is the B, and say it is a current, rate of charge is the current, these 3 are mutually perpendicular directions. That is, let's say it is I as the B and automatically it is F. You can remember it is very easily. FBI, American Detective Agency. American Detective Agency, Federal Bureau of Investigation. Federal Bureau of Investigation. That's the Fleming's left-hand rule. With that, you can find out the force acting on the charge which is kept in a magnetic field. Instead of this charge, if you keep a conductor in, we will get the same results. Instead of that, imagine a conductor is kept like this, okay, and we have to find out force experienced by the conductor. Already we learned that F bar is equal to Q of V bar cross V bar. It's the Lorentz force, and the magnitude of the force is equal to F is equal to QVB sine theta, okay, but Q is equal to IT. If you put the value in, what you get? F is equal to IT multiplied with velocity. Let's say the length of the conductor is L. Velocity is equal to L by T into B multiplied with sine theta. TT get cancelled, and we get F is equal to Bill sine theta. Is the force experienced by the conductor, and we will get the values of maximum and minimum forces. What we got earlier. Here, keep the theta as 0. Means what? This conductor, this one, is flipped like this. It is parallel to the B. Then theta is equal to 0. Automatically, the case will be F is equal to Bill sine 0. Obviously, it is 0. That means what? If a conductor is moving along the direction of the magnetic field, the force experienced by the conductor is equal to 0. Okay, and if it is moving in this way, it is perpendicular to the field, then you can get the force. Again, theta is equal to 90 degree. That is F is equal to Bill sine 90. It is equal to Bill, and it is the maximum force. In this way, we can find out minimum and maximum force when a charged conductor, that means what? A conductor with, in which the current is flowing, is kept perpendicularly and as well as the parallel to the magnetic field, or with any angle. If maybe it is 0 to 90 to 180. Just imagine that this conductor, instead of kept like this, is flipped here. Then it's making an angle of 180 degree. As you know that sine 180 is equal to 0. If the conductor is moving along the direction of the magnetic field or opposite to the magnetic field, it experiences 0 force. I hope you understood the concept very well. And my suggestion to you, watch all the videos till the end. But I showed a message. Students, generally people feel that the magnetic effects of electric current is very tough, truly. But if you listen it in a right way, it will be very easy. And to understand this concept very well, you have to know a little bit of vectors also. If you know about the vector notations, you will understand the topic very well. Already I use the vector notations, but in coming videos. And one more thing, to understand this concept well, please watch the video till the end. My advice is watch the video till the end, then only you will understand the concepts clearly. Otherwise, I can't say.